Chapter 2. Overview of Special Relativity. In the realm of physics, the term relativity might sound complex, but at its heart, it's about how we perceive and measure time and space. Before Einstein, our understanding of these concepts was largely based on the work of Isaac Newton, who viewed time and space as absolute and unchanging. However, Einstein's theory of special relativity introduced a revolutionary idea. Time and space are not fixed. They are relative and intertwined. Time dilation. Imagine you are sitting in a train, moving smoothly along the tracks. Inside the train, you feel at rest, comfortably reading a book or gazing out of the window. To you, the journey seems peaceful and uneventful. However, to someone standing by the tracks, watching the train whiz by, you are moving at a considerable speed. Einstein proposed that time itself flows differently depending on your motion. This phenomenon is known as time dilation. To illustrate, consider a spaceship traveling close to the speed of light. For the passengers on the spaceship, time passes normally. They can go about their daily activities, unaware of any difference. However, for observers on Earth, the spaceship's clocks appear to tick more slowly. Imagine the spaceship embarking on a long journey across the cosmos, exploring distant galaxies. For the astronauts, only a few years might pass, filled with discoveries and adventures. But when they return to Earth, they find that decades, or even centuries, have passed. Their friends and family have aged or even passed away, while they have remained relatively young. This is not science fiction. It's a consequence of the laws of physics at high speeds, where time itself stretches and slows down relative to the observers at rest. Length contraction. Another surprising result of special relativity is length contraction. This concept suggests that objects moving close to the speed of light will appear shorter in the direction of their motion to a stationary observer. Imagine the same spaceship, traveling at a fraction of the speed of light. To the astronauts aboard, the ship's dimensions remain unchanged, providing them with the same living and working space. However, to an observer on Earth, the spaceship appears contracted, squeezed in the direction of its motion. This phenomenon is like watching a fast-moving car appear shorter and more compact as it speeds by. If you were on that fast-moving spaceship, you wouldn't notice any change in size, but someone watching you from Earth would see the spaceship as if it were being compressed. The speed of light. Central to special relativity is the idea that the speed of light is a universal constant. Regardless of the motion of the source or the observer, light always travels at the same speed in a vacuum. This constancy leads to the conclusion that nothing can travel faster than light. It also means that time and space must adjust to ensure this speed limit is never breached. Imagine holding a flashlight and pointing it ahead of you as you walk through a dark room. No matter how fast you walk or run, the beam of light always moves away from you at the same speed, illuminating the path ahead with unwavering consistency. This seemingly simple observation has profound implications, leading Einstein to realize that the fabric of space-time itself must bend and warp to maintain the speed of light as an unchanging constant. Putting it all together. Special relativity might seem counterintuitive because it challenges our everyday experiences. We are used to thinking of time and space as separate entities that tick away independently, but Einstein showed us that they are part of a single fabric known as space-time, and that our movement through this fabric affects how we experience both time and space. Imagine space-time as a vast, flexible sheet. As we move through it, our speed and direction cause the sheet to stretch and bend, altering the way we perceive the passage of time and the dimensions of objects. This interconnectedness of time and space forms the foundation of special relativity, revealing a universe far more intricate and dynamic than we could have imagined. In the next chapter, we will dive into general relativity, where Einstein extends these ideas to include gravity, showing us how massive objects like stars and planets can warp the fabric of space-time itself. This next step in our journey will deepen our understanding of the cosmos, guiding us through the mysteries of gravitational forces and the very structure of the universe. So, as we continue our exploration, let your mind relax and wander through the vastness of Einstein's insights, finding peace in the elegance and simplicity of his revolutionary theories.